Hello and all present here. In this lecture video, I am going to tell about the continuation of the critical section problem, that is Peterson solution. We already know what is critical section. It is nothing but each process which has a segment of code which will be naming as critical section and which has three sections, that is entry, exit and remainder section, and we saw the general structure of the critical section as well. Now we are going to see about the Peterson solution, which is actually illustrated with the help of classic software based solution to the critical section problem, which we are defining it as Peterson's solution. It has this is restricted to only two processes that alternate execution between their critical section and remainder section. Okay, what is Peterson solution in OS actually is? We already discussed it's actually a classical solution to the critical section problem, which ensures that no two processes change or modify a resource's value simultaneously. Say for example, if I am giving as integer a is equal to 5 and there are two processes P1 and P2 which can be modified the value of a. P1 adds to a adds 2 to a and a is equal to a plus 2, and P2 multiplies a with 2, a is equal to a star 2. If both processes modify the value a at the same time, here condition comes the race condition problem. Then which value the value depends on the order of execution of the process. If P1 executes first, the value of a will become 14. If P2 executes first, the value of a will become 12. So this change of values due to access by two processes at the same time is the cause of the critical section problem. No two processor can able to read at the same time or write at the same time. So we are going to have two things as P1 and P2. P1 is equal to 0 and P2 is equal to 1, and we are just going to allocate which process has to be in the critical section. There is a chance for P0 to give the authority to P1 even if P0 is willing to enter into the critical section. Similarly, there is a chance for P1 to enter into the critical section, whereas it can also have the authority to give chance for P0 as well. So we are going to use a flag variable here. We are going to check two conditions, flag of j, and if turn is equal to j means I'm just giving chance for P1 to enter into the critical section. Once the P1 process over, it reaches the exit section, and the remainder section will have the remaining code. So this is actually the structure of process P1 in Peterson's solution. Peterson solution, again I am saying the requirement is the two processes, it can easily share two data items. I mean, if it is know the order on which it is entering into the critical section, easily we can solve the problem. Without data inconsistency, it should give the solution. So it has to take care of all these three conditions. One is mutual exclusion is preserved, and the progress requirement is also satisfied, and the bounded waiting requirement is also met. The next second problem is called as synchronization hardware. So the solution can be in terms of hardware instruction which are available on many systems and which show how they can be used effectively in solving the critical section problem. Here we are using a concept called as locking, protecting critical section region through the use of locks. So we are going to use a multiprocessor environment. Test and set is one function and compare and swap is another function. So this is the definition of test and set. Here, if test and set and we are giving lock as 0, it can enter into the critical section. If lock is equal to false, it is entering exit from the critical section. So until while loop becomes false, the loop will be executed. And compare and swap, we can just compare the new value with the swapped value. So here also, if it the lock is not equal to 0, if it is 1, it can enter the critical section. If lock is equal to 0, it can directly move to the remainder section. So here is the coding of this bounded waiting mutual exclusion. Thank you. Next we will see about the mutex locks.